Okay, this is lecture 16, part 2 on Quadrature Amplitude Modulation and Reception and Receiver Design. This is the spring 2014 class on Real-Time Digital Signal Processing Laboratory at the University of Texas at Austin. So in part 1, I covered briefly the block diagram for QAM reception, and these are the topics for the whole 2 parts here. So for an introduction, automatic gain control. Today we'll do the remaining subsystems, carrier detection, symbol clock recovery, channel equalization, and finally the demodulation step. So I left off with I covered the block diagram last time, and so let's kind of go back through that quickly. So the block diagram is fairly complicated now in the receiver. The receiver has an awful lot of work to do compared to the transmitter. So there's a lot of blocks in this block diagram, so let's kind of go through it quickly again. So the transmitter, its job is to get a bunch of bits ready for transmission. We'll do that ultimately by grouping the bits into J bits, looking up an in-phase and quadrature amplitude value from our constellation map, and then do the usual pulse shaping. And because it's quadrature amplitude modulation, we have to have up conversion. This allows us to put 2 PAM signals in the same transmission bandwidth. So we recover this loss of this doubling of transmission bandwidth and up-converted PAM, but now we're putting 2 PAM signals in that same double the transmission bandwidth, so we recover back that factor of 2. Finally, we go through a D to A converter, and this is still a baseband signal. Now it's band pass, which is interesting. It's baseband, and that its energy is centered around 0 frequency, but it's nonetheless still, you can think of this as a band-pass signal. Now, it's still baseband transmission, but again, the DC component is going to be 0 or something very small here, right? Because of the up-conversion step, the bandwidth here of S of t, this is now my baseband signal, one in discrete time, little s of m, and continuous time, little s of t. So the spectrum looks something like, it depends on carrier frequency and the pulse shape and so forth, but it's something like this. Right? So it's going to be, again, the energy is centered around 0 frequency. We still call this baseband, even though it's got a bandpass shape. Again, just because energy is centered around DC. That's the transmission side, and we spent lecture 15 on this in 2 parts. Now, for the receiver side, we've got kind of 2 different ways to look at this, and they're both interesting and complementary. The first is the signal path. So if I look at the received signal, R0 of t, it's going to undergo a series of, really mostly filtering, honestly, some version of filtering all the way through this signal path. And so along the signal path, we're going to be taking this received signal, R0 of t, and doing certain, processing steps on it, until we get out an estimate of the in-phase symbol amplitude and the quadrature symbol amplitude. And then from there, we can make a decision at the very last step as to what bit pattern was most likely to have been transmitted. So this is, I have to know both the estimate of the in-phase amplitude, symbol amplitude, and the quadrature symbol amplitude. And using both of those pieces of information, I make a decision as to what bit pattern had most likely been sent. Now, this is the signal path. This is what the received signal undergoes directly from the input to the receiver to the point where we're making a decision in the receiver. Now, there's a lot of stuff on the side, and it's very, very important stuff. Automatic gain control, covered this last time in part 1 here of lecture 16. Carrier detection, which is today, symbol clock recovery. Now, in the signal path, I've got an equalizer. That equalizer is what kind of filter? Is it FIR or IIR? What's your guess? Adaptive. Yeah, FIR. So we can do adaptive infinite impulse response filters, but what do you think the problem is with adaptive infinite impulse response filters? Stable. So for here, maybe a long time to train, possibly. Bigger problem, stability. All right, so adaptive IR filters do get used in practice in some applications, but rare in this case. We're commonly using an FIR filter Again, the issues here are stability is the big issue. So there is a subsystem off to the side not shown here, which is to design those FIR coefficients. And we'll talk about that design today. Off to the side, we also have not shown in this block diagram some ability to figure out the carrier. In this case, it's at the baseband frequencies, but the carrier frequency and its phase. So it has to be some sort of carrier frequency estimator and phase lock loop. Part of the deal with QAM, we're sensitive to phase error. We have to use a phase lock loop most likely in our system, but not shown here. All right. So a lot of stuff off to the side that's setting parameters for our different blocks in the signal path. Again, signal path is in blue, and I use this term a lot. So this, and you'll see it on tests and so forth. Again, the signal path is in blue. It's what the received signal directly undergoes in terms of operations, mostly filtering of one kind or another, but not always, not exclusively. And then we all these subsystems off to the side, computing parameters to feed into the blocks on the signal path. You've got to get those right. Now, there's a lot of intellectual property here. So if you look at where are the patents, where's the market, where's the differentiation in one product versus another, what makes a company have success with their technology on the technical side, and it's in these blocks. So it's in the receiver design. Synchronization is a big one. Equalization is a big one. It does depend on the standard. Certainly, which of these blocks plays a big role. But these two are automatic gain control is also another one. These have and carrier, frequency estimation and phase lock loops. These all have a lot of patents that go with them. So this is where the intellectual property is. And if if you go to work in industry, or when you go to work in industry, most likely some will become professors here eventually. But for those that don't, a real value you have to the company that you work for is to file patents. And in a patent portfolio, each patent can be valued at roughly $1 million. This is a big advantage to a company, having a good patent portfolio, both to defend against lawsuits, but also to countersue or file lawsuits as well. So this is on average. Some patents actually don't really have any value intrinsically or even extrinsically. Some has to be gone through some sort of patent lawsuit. But the patents that really matter are worth an awful lot of money. So I've seen patent lawsuits over 6 patents, $100 million. Okay, so those 6 patents really mattered. Other patents may not have mattered. So a company would rather have a big portfolio because they don't know which one's going to really matter in the end. So you file, and you wait for the litigation to decide which ones are really important, and at least in terms of financial settlements, which ones are the most valuable. All right. So in this space, it's mainly in the receiver. It's these blocks that I've kind of checked off, plus carrier frequency estimation and phase lock loop. On the transmit side, not as much, not so much here, although there's quite a bit on the data converter side, which I actually didn't even put down either. So there's a lot of intellectual property here on the data converters. On the transmit side, not as much here, not as much differentiation. So in a communication system standard, usually the standard carefully defines what the transmitter is supposed to do. And the receiver has flexibility on how it decodes that transmission. Some flexibility on how it decodes, but the transmitter is pretty well defined. And a few things you can do, the data converters, there's some analog front ends, there's intellectual property there, maybe some echo cancellation, some different things in the transmitter. The bulk of your IP is going to be in the receiver for two-way communication where it's symmetric, where the transmitter and receiver are equally capable. It's going to be in these receiver subsystems. For a base station handset situation, a little different game. All right, both are at play in different ways in the cellular space. But for kind of symmetric two-way communication here, even down to a Wi-Fi plus access point. So these things are very important. So we'll talk about these as we go today. Any questions on this block diagram from last time? This is a big one. So Lab 6 is a top block diagram, and in the demonstration there's or in the website, on the website there's a lab view demonstration of QAM transmitter. All right, so you can download, run it. Don't need to change anything, just hit the go button. Hit the right arrow button if you're in LabVIEW. Okay, any questions on this? Okay. We did automatic control, so let's do carrier detection. This is the simplest system, actually, of the blocks that I have in that block diagram, or at least this method for carrier detection is the simplest of all the ones we'll talk about today and that we've talked about yesterday, or sorry, on Friday. So the carrier detection here has got two roles to play. One is, and it's always going to be running. All right? And because it's always running, we like to make it power efficient or energy efficient. We don't want to waste power or energy here. So a simple way to do, remember, the carrier detection is after the receive filter, which is a bandpass filter, after the A to D converter, which has another low-pass filter in it. There's already been a fair amount of filtering by the time we get to the carrier detection. We want to detect the energy of the received signal to make sure that it is above a certain threshold. And that threshold will depend on whether, if there's a connection that hasn't been made, that threshold may be somewhat high, waiting for enough energy to come through and say, there's a connection trying to be established. If I have a connection, then I might lower that threshold quite a bit. And now I want to detect when is that connection finished, when is the other side hung up, terminated, what have you. So we're just going to do the simplest thing. We're actually, interestingly, it's called carrier detection, but for this method, we're not going to focus on the carrier frequency or the transmission bandwidth. Explicitly. Now, implicitly, before we even hit this block in the block diagram, again, the receive signal has gone through a bandpass filter, receive filter, to pass the transmission band frequencies, attenuate frequencies outside the transmission band. It's already been bandpass filtered. And in the A to D, it's been low-pass filtered. But a band that's wider than just the transmission band. Okay, so what we like to do is simply detect the energy. How much energy are we seeing in the received signal? How much is there? And a very simple way to do this is I could certainly just keep a running sum. Remember, I'm in discrete time. I'm looking at the output of the D to A converter. So as the block diagram goes, I have my, A to D. So I have my A to D converter in the system, and off to the side is my carrier detection. So my carrier detection, again, it's after bandpass filtering, automatic gain control, A to D conversion. And this has some number of bits, running at a sampling rate. Okay, so simplest thing I can do is just detect how much energy I'm seeing, and I can certainly do an integration over all time. But what's the problem there? Stability. Yeah, I'm not Bible stable. So let's see if we can come up with another way to do it, which is now, so what was the fast implementation of a running summation? We simply took, so consider the running summation all the way back to homeworks 1 and 2. Remember, the fast implementation for running summation was its output is just the previous output plus the current input value, right? That was the fast way to do running summation. But as you just pointed out, this is not bivostable. Okay? So as an alternative, what we can do now, as an alternative, we can take a weighted sum, which is what we'll do. We'll take a weighted sum of the input and the previous output. This weighting will, in the end, give us a low-pass filter. We'll give away one of the questions, but it's a low-pass filter. Okay. And now the input, which is, for our particular case, the input's going to be power. So x of n, so in our case, x of, I should go with a little m just for consistency here. Let me do that. The input is simply the value here of R of m squared. All right, so this is the, how would you describe this in words? What's R squared of m? What's that measuring? Magnitude of the received signal, magnitude squared? Yeah. R of m is real values, right? So it's the same as magnitude squared. but what quantity is that? You know, if R of m is a voltage, which it is, then it's power. It's the instantaneous power. It's the power at index little m. So the kind of good news here is that x of m is always non-negative. It never goes negative because we're doing r squared. Now, if we do a weighted combination, we'll see that this is a smoothing filter, and we'll derive the transfer function in just a second. Okay, and c is some constant in the sum of a weight, so I'm going to take c times the previous output value, and I'm going to take 1 minus c times the current input value. Now, the input value at the present time is, again, r squared of m. So it's instantaneous power. So we're going to smooth those instantaneous power estimates with time, filtering. Okay, so let's get the transfer function out of this. And again, I'm going to go back to let x of m, I'm going to replace r squared with x of m just so it's easier to see the relationship. That's more common to what we've been doing in the past. So again, I have a difference equation. And so what I do, I take my difference equation to get the transfer function, take the z transform of both sides, right? And so I get pretty familiar stuff, p of z there, c times z to the minus 1, right? Capital P of z, I'm delaying in time by one sample, multiplied by z to the minus 1. What's the rest of this? Plus what? What's the next term? 1 minus c times x of z. Now, all I have to do is get this under or over a common expression with, so I just, it's a first order, you kind of see this, it's a first order IR filter, right? I've got just the one delay term here. So this is a first order system, right? One feedback term, and it's only I'm only feeding back the previous output value. It's first order IR filter. And so the transfer function here, go back up here. So the transfer function, again, I just take the term over here and divide by both sides. I get P of z divided by x of z. And really by inspection, you might be able to get this. It's just a first order system. You've worked a lot of these. So I get in the denominator, what am I going to get? 1 minus, I heard c, z to the minus 1. And what's in the numerator? Just 1 minus c. There's no dependence on z. So you think of some extreme cases, right? When c is 0, then it's not very interesting when c is 0. Yeah, it's input equal output, right? When c is 1, output, I'm just not following the input at all. All right, so let's look at where the pole, what's the pole location? Pole is where? Pole is at? You can read it right off. Right? What's the pole location? C. So this determines, remember, C is real values. C is a real number, and it's positive. We're not going to let it be 0 or 1, but between 0 and 1, non-inclusive. So I have a real pole. The value is not positive, between 0 and 1, non-inclusive. So what value C would you recommend? From a filtering point of view, something close to 1. You like to have a stronger response, if you will, more selectivity. So you could do C of what? Give me a value. 0.9, fine choice. So how about 0.9? It's a pretty good one. All right, now let's make it another choice to make the implementation easy. How would you make the implementation easy? 1, we don't allow 1. That would make it easy, but we're not allowing 1. Give me another value. Now, the hint here is that the input's always non-negative. So we can play some nice games here with the multiplication. We can replace the multiplication with a right shift if we're in 2's complement. Right, so you divide by 2, it's a right shift by 1. Divide by 4, it's a right shift by 2. 0.5, not bad. Pretty good. So 0.5, pretty good choice. Now I multiply just a right shift by 1. When I multiply by c, when I multiply by 1 minus c, it's also a right shift by 1. I've removed the multiplier. And even if I have 1 on chip, which I do on our processor, it's pretty power hungry. So again, if we want to really reduce power while we're listening to the environment, getting rid of the multiply operations is a good idea. Now I can also do 0.75. How do I multiply by 0.75? How do I multiply by 3/4? I multiply by half, and I multiply by 1/4. And I add them up. So I can do a right shift by 2 and add that to the result if I right shift by 1. So 0.75 is a pretty good choice. Now 0.75 also gets our pole location closer to the unit circle. So 0.75 is a fine choice. Nice smoothing filter, better than 0.5. Not as good as 0.9, but again, the complexity advantages here at 0.75 are pretty good. So that's the one we want. There's flexibility in what value of C to use. Okay, again, there's the 2 uses I mentioned earlier. They're here in the bullets. Again, if a receiver is not currently receiving a signal, then we look at the output of this energy detector. And if it's larger than a large threshold, then we assume we're receiving transmission, and we start going through the process of symbol recovery and all this stuff. There's no reason to do all that work in the receiver if I'm not receiving anything. So this is just a way to find out if there's something going on that might be a transmission. And if there is a transmission going on, then so if a receiver is currently receiving a signal, then it detects when the transmission has stopped. And again, we're going to compare the output of the energy detector. And if it's smaller than a small threshold, then we're going to say that we've stopped receiving. Okay. Good, more or less. Good connection with the first half of the class. Okay, now talk briefly about symbol clock recovery and then refer you to the details in the course reader. There are many methods for symbol clock recovery, and you've looked at some in lab, and you've also seen other ways we can recover clocks. So we've talked about preemphasis and bandpass filtering to emphasize or pull out a particular clock frequency from a transmission. The symbol clock here is going to be, if you remember in terms of where the frequency is, it's going to be, depends on the pulse shape, but we know we got half the symbol rate there in the transmitter. Right, the transmitter has has upsampling or impulse modulation, where we get those impulses that are spaced at the symbol time. In other words, there's a sampling effect here at the symbol rate. And in the discrete time implementation, we would upsample to convert symbol rate to sampling rate. So there is so if you remember, what's the fastest, continuous time 2-PAM signal that we can have? And it's going to be this alternating. So if I have symbol amplitudes are alternating plus D, minus D. So consider the most extreme case, plus D, minus D, plus D, minus D, etc. That's the fastest alternation that we could have in 2-PAM. Okay? And that corresponds to if we neglect the pulse shaping for a minute, this is going to correspond to, if we look at upconverted, so what is this, what's the rate that we have here alternating between plus D and minus D? It's going to be at half the symbol rate. Okay, so let's think about why that is. All right, so if we do, am I doing this in continuous time or discrete time? Right, so we have minus D right, so if we think about a cosine, right, and I want to look at the discrete time version of this. Remember, this is our symbol rate. And so if F naught is half the symbol rate, then this cosine is going to give me, sorry, I missed the sampling here. So my cosine here is going to be cosine pi n, right, when F naught is half the symbol rate. So I'm going to go from plus 1 when n is 0 to minus 1 when n is 1, plus 1, minus 1. And so all I have to do is, to get the plus or minus d, I just have to multiply this cosine by d. And I'm going to alternate between plus d, minus d, plus d, minus d. Okay. So the highest frequency that we're going to see, again, the pulse shaping can expand this. If we use a raised cosine pulse, then the actual frequency content at baseband will be 1 plus alpha times half the symbol rate, where alpha is between 0 and 1. But we are going to include half the symbol rate. We're confident about that by the time we see the transmitted signal in the receiver. Okay, so what we're going to do in the receiver, and for this particular one, it can be tuned to either QAM or up-converted PAM with a carrier frequency. Either one will work. So what we're going to do is have two IR filters that will be bandpass, single pole, and one is going to be tuned to the carrier plus half the symbol rate, and the other one's going to be tuned to the carrier minus half the symbol rate. So these are the min and max frequencies that are possible in transmission that we know are there. Again, with more pulse shaping, we might have more frequency, but we know we have at least this much in the transmission. And the bandwidth here depends on your context, but the bandwidth here tends to be pretty low. You want to really lock on to these clock frequencies as best you can. And the bandwidth here is going to be dependent on what? I've got a single pole bandpass filter. I have one pole. I have a single pole filter tuned to this upper frequency. I have another single pole filter tuned to lower frequency. How do I determine the bandwidth? What's my only freedom here in the filter design? Position of the poles. And how's that going to affect bandwidth? As the pole gets closer to the unit circle, what happens to bandwidth? It's going to reduce the bandwidth, be more selective. So again, there's a trade-off here. How again, 0.9 is probably a good starting point, but you have to figure out more of whatever bandwidth you need to match it. Now, these poles are going to be complex valued. Remember, I have. So what is this frequency? This frequency is, this is the single pole. All I can do is, it has to be complex valued, right? So if I want to design my pole locations, so we ultimately discrete time implementation. So it's after the A to D conversion. Ultimately, my poles are going to be out here. And this frequency, actually, I'm going to change that. The pole locations are actually here and here. So one is going to be tuned, so the upper one will be tuned to the carrier plus half the symbol rate. And the lower one, this is an L, not a 1, the lower one will be tuned to the carrier minus half the symbol rate. These are complex valued poles. This is the one case I'd mentioned early in the semester where we have a complex valued infinite impulse response filter. The coefficients are complex valued and pretty useful. Now we're going to combine the output of these two filters in a nonlinear way, and that's what kind of makes this algorithm work. And the handout has the details on it, but we're going to multiply the outputs of the two filters. We're going to multiply the upper bandpass filter with a conjugate of the lower bandpass filter. And it turns out this will unlock an estimate of the symbol timing error in the previous symbol time. Or you can say the current symbol time that will feed back to use in the next symbol time. So this gives us the following. It gives us actually, if you're working through the math, we actually get this expression. We get an expression that comes out of this multiplication that's a sign of the symbol rate, the one we're currently using, and the symbol error tau. And again, using a small angle approximation, then you can say that the argument of the sign is approximately equal to its argument when that argument is close to 0. Now, it turns out these estimates of this error, so I have to divide by omega sim to unlock the symbol rate that I'm using to unlock the symbol timing error tau. Now, these estimates are prone to error, susceptible to noise. So we're going to apply a filter to smooth that out, a first order filter, very similar to the energy detection case. I'm going to have a weighted sum of the previous estimate of the symbol error and the current estimate of the symbol error. And these weights, alpha and beta, will tell me which one do I take more of. And again, this is just going to be a low pass IR filter. Alpha and beta are real valued. This is a standard real valued, standard first order IR filter, one feedback term. So the output of this smoothing filter is the timing error estimate to be used for the next symbol time. So it means I'm going to advance or delay the taking of the next symbol by tau. It tells me the value to advance or delay the clock so to help align the transmitter's symbol clock and so the receiver symbol clock with the transmitter symbol clock. Okay, so this is not an adaptive algorithm in the sense that we're not doing steepest descent or conjugate gradient. Any least mean squares here. It's a fixed filtering approach that combines linear time invariant filtering with some nonlinear operations to make this work. But it does provide an estimate every symbol period of the timing error in that symbol period, which can be used in the next symbol period. So in that sense, it will track the symbol error with time, but it's not adaptive in the sense that we've talked about in other cases. These are fixed coefficient designs. Any questions on this? Okay, so please see handout. This is I think the good old method, the GOOD-ALL method for symbol clock recovery. But handout M is a Mary or Mark in the course reader, has the details. All right, let's do channel equalization. This is homework 7, due on Friday, due in 2 class periods. All right, so for channel equalization, we have a lot of work to do. This equalizer in the receiver has got to mitigate linear distortion in the channel. This linear distortion has a couple of different effects to it, and both are significant. Now, for the purpose of this discussion, we're going to place the equalizer right after the A to D converter, as we saw in the diagram, previous block diagram on slide 16-4. Sorry. So there are 2 issues with the linear effects of the channel on a transmitted signal. The first is, again, we just maybe talk about linear time invariant effects here. In the time domain, we know that there'll be a spreading in the time domain due to a convolution of the channel impulse response and the transmitted waveform. And that spreading is going to mean that I interfere with future symbol transmission, or simple future data transmissions. Intersymbol interference, which we talked about in the past. We'd like to get rid of that intersymbol interference as best we can. We won't get rid of all of it, but we can get rid of a lot of it. The second impact that the linear time invariant part of the channel has is that there's a frequency distortion, right? So that impulse response also, it reflects in the frequency domain that I'm going to alter magnitude and phase of the transmitted waveform as it goes through the channel. Now, more than that, those are LTI effects, or linear time invariant effects. In practice, that channel is going to vary a little bit with time due to simple propagation of the waveform in the media. And we also have additive noise in all of this to worry about. So our equalizer often needs to worry about amplifying the additive noise that's there, which is another side to worry about in all of this. For this discussion, we're not going to worry about the additive noise for this particular discussion. We're just going to go after the filtering effect in the channel that can be modeled as linear time invariant or even linear time varying, and we'll get the linear time varying part by adapting the equalizer with time. So I track the, if you will, the changes in the frequency response over time. The channel model we'd like to have, or at least with the equalizer will try to get us to, is this channel model, which I haven't mentioned yet. Right? This is another ideal model. I did mention this briefly. I take that back. So this is another ideal model, and it's less than a full filter, but more than a wire. But we can undo this in the receiver. So the ideal channel, the equalizer is going to try to make the what the equalizer is going to do is try to make the channel look like this, even though it's not going to look like this. So this ideal channel is a cascade of a delay delta and a gain G. Now, how do I undo the gain? What do I do at the receiver? By 1 over G, right? Multiply. So to the precision of the multiplication of G and 1 over G in the receiver, we can undo this. How do I undo the delay? By delta samples. What do I do? Yeah, how do I get rid of the delay? Sure, I can get rid of the delay. How do I get rid of it? Shift it, and then as an implementation, what do I do to shift it? Make a buffer? Better than that. Yeah, throw away the samples. How many? Well, that's for linear phase. Now, I have some bad news. In the channel, we're not going to get nice linear phase filters in general. They're going to be really ugly phase filters. Okay. But hopefully my equalizer will do is give me an equalized channel that looks like this. So how do I do this? How do I undo the delay by delta? Get rid of a certain number of samples. How many samples do I get rid of? Delta. Yeah. So I just throw out delta samples and I'm good. Right? Because now I don't have to worry about what the initial conditions were, which I have no control over anyway. That's in the channel. Just throw away delta samples and I'm good. All right. What is all the answer there? Okay. All right. So again, if I look at what happens if this ideal channel, think about the effect of this ideal channel in the time domain, it's just an impulse. If I look at the impulse response of this in discrete time, what is the impulse response of this ideal channel? Well, it's just a delayed impulse scaled by G. That's all it is. So that's the ideal response as an impulse response. Scaled, delayed, discrete time impulse. The frequency response of this ideal channel is all pass. All frequencies pass through. Just a delay. no frequent, there's not a low pass, right? It's just a delay. It's all pass. Everything's getting through. And linear phase. So that if we could have that channel, that's great. If I'm transmitting through an all-pass linear phase channel, this is good. It's a good channel to have. Now, how do I get there? Okay, also want to alert you to some good midterm 2 questions on this. I'll look at the last couple of, maybe the last 2 or 3 midterm 2s. As you're getting ready for homework 7 or looking through homework 7. All right, so here's the setup. We have a discrete time baseband system. I have a transmitter that's going to transmit X of M. And at some point in the connection, I'm going to set a training sequence. Training sequence will be, what do you think? Pseudo noise. Yeah, most likely pseudo noise. Something looks like it. Usually it's pseudo noise in practice. So there's some pseudo noise, some known training sequence that's easy to regenerate in the receiver. So the transmitter sends its training sequence down through the channel. We're modeling the channel here as some sort of LTI system filter and additive noise, but again, in the formulation, we're going to ignore the noise for this particular formulation. I have an FIR filter in the receiver. So now here's my receiver. And now my job is to train or design those FIR coefficients so that I undo the frequency distortion in the channel. My job is to inverse filter, essentially, the filter H in the channel. Essentially, that's my job for the equalizer. So if my channel is low pass, my equalizer should be high pass, because I would like to have the cascade of the channel and the equalizer be all pass to look like this ideal channel that I just mentioned to you. And I show you again here in the block diagram. So I have a dashed line here. This does not exist. This is our model. This does not really exist. It's what we'd like to have. Does not physically exist. It exists in our model, in our minds, in our abstraction. So at the receiver, I'm going to regenerate the same training sequence. And go ahead. That gain is a result of the channel and equalizer. That's correct. Now, we can set the gain to 1, which we'll do in the homework. 7.1, 7.2. And we're going to search, because we don't know the delay. We don't know, this delay is a transmission delay. We don't know what that is. Now, we can have an idea what that is, because I can correlate the training sequence sent by the transmitter against the regenerated PN sequence at the receiver and find the transmission delay. So I have some idea what this is. Now remember, this is a transmission delay after equalization. So it's the transmission delay through the channel plus the group delay through the equalizer. Now I have some bad news. The equalizer will not be linear phase, most likely. So the formula is n minus 1 over 2. Doesn't work so well. It's a good formula for linear phase, but we don't have linear phase here. All right, so in practice, we're going to use an FIR equalizer, and we're going to adapt it. Now, we could also use an IR equalizer, and I give you the way to look at that here. So if we use an IR equalizer, and we ignore the noise for a second, what we'd like to do is ultimately set the error to 0. So if you look at what's computing, so on the upper path, this is the signal path. So on the signal path, which is this one, I want to know how close I can force the actual equalizer that I have. How does that compare against the ideal channel that I'd like to have? And the difference between the two output values is our error. It's a difference. We'd like to drive the error to 0 if we can. So we'd love to make that error 0. We'd love to have the equalizer give us an equalized channel, that is, by equalized channel I mean the cascade of the channel and the equalizer, to look like this ideal channel below. That's our hope. We won't get there exactly typically, but we'll get close, almost arbitrarily close. All right, so in order to make this error 0, then what I'd like to do, if I ignore the noise for a second, I would like to have the upper branch, which is the cascade of the channel, capital H of Z, and the equalizer, capital W of Z, equal to the transfer function of the ideal channel below, which again is just G times Z to the minus delta. Again, where delta is a constant integer and G is a real number, not 0. Well, this one's pretty not bad. So if I know the transfer function of the channel, the LTI component of the channel, then I can just divide both sides by that to get the equalizer transfer function, and from there I can get the coefficients. So for example, if H of Z were FIR, then H of Z would go in the denominator. So the zeros in the channel become the poles in the channel. See any problems with that one? Stability again. Stability is a problem. The good news is you've learned how to deal with this in the first half of the class. If I have poles, remember, what I really want is the cascade of these two filters, the channel filter and the equalizer filter, to be all pass. I really want an all pass system. What I really want is the magnitude of the cascade here to be G. That's what I really want. All right. So if H of Z has zeros, has a 0 here, where do I put the pole of the filter for an all-pass response? I want an all-pass response when I cascade the channel equalizer. So where do I put the pole location? Almost equidistant. It's 1 over. Right. So if the distance is r, so if this distance is r, then this distance is 1 over r. Remember that from all-pass filters? So again, I have, here is, so I have 0 in the channel, and then my pole in my equalizer would be there to compensate. Okay, what happens if the 0 location were already inside the unit circle? What would you do? Where'd you put the pole? Right on top, right? So you get a cancellation. Cancel it out. One more case. What's the last case? Wow, the origin's not so bad. On the unit circle. Yeah. All right, let's do that. Just put a couple of zeros on the unit circle. Now what do I do? What's the best thing I could? What's the best I could? I can't. What if I put the poles right on top of the zeros? What happens? Bible unstable. So what can I do? Put them really close, and what kind of filter do I get? A notch. Remember, a notch filter is all pass outside of the notch frequency and a small band around the notch frequency. So the best thing I can do is to put a pole as close, maybe radius 0.9, but in the same angle as the 0. Okay. So given an FIR channel model for the LTI component, I can give you the IR equalizer. And it's all pass except wherever the zeros, in the channel or on the unit circle. Then I can help you with. I can't help you right around that frequency value. Go on.
So why don't you really care about phase response?
Well, remember the phase response. It depends on the. So why we care about phase? It depends on the modulation method. So for QAM, phase really matters. For PAM, not so much. Right. So 45-degree error in PAM, I'm fine. QAM is sensitive, and that sensitivity, I have to get a smaller phase error as my constellation grows in size. Okay, so it's possible you don't care much about phase. We do care about magnitude of response, certainly. We certainly want an all-pass response here. Now remember, we're not going to. This cascade won't give me linear phase per se because of the notch filters. The effect of basically the equivalent, the equalized channel is a notch filter. But I should get a lot of linear phase outside of, over some frequencies. Some of the bands. Oh, Lord. All right. Okay, we're going to have a part 3. No way to do this one. Okay, see you on Wednesday.